Hello, my dear friends. First, we are going to study about the synchronous counter. In a synchronous counter, first we will learn about 3-bit synchronous counter. 3-bit synchronous counter can be prepared using the 3 flip-flops, and the output will be from 000 to 111. That's why it is called 3-bit synchronous counter. What is the difference between synchronous counter and ripple counter? The ripple counter is simplest to build, but there is a limit to its highest operating frequency because its settling time is going to be larger. So its frequency of operation is going to be limited. That is one of the limitations of asynchronous counter or ripple counter. As previously discussed, each flip-flop has a delay time. In a ripple counter, these delay times are additive, and the total settling time for the counter is approximately the delay time times the total number of flip-flops. That means settling time is very large. It is increasing as the number of bits are going to be increasing, as the number of flip-flops are going to be increasing. Each flip-flop propagation delay time is going to be additive. Furthermore, there is a possibility of glitches occurring at the output of decoding gates used with the ripple counter. Unwanted glitches or unwanted signals are going to be produced in a ripple counter. Because of that, what happens? Actually, when you are utilizing a asynchronous counter or ripple counter in a digital system, because of these glitches, the further circuit can be false triggered or triggered at unwanted time, and hence the operation is going to be unauthorized. Next, the first problem fully and the second problem to some extent can be overcome by the use of synchronous or parallel counter. That means both these problems, one, the speed of operations is going to be increased in a synchronous counter, and glitch problems can be eliminated in a synchronous counter. Hence, we are preferring the synchronous counter. But the difference is this: in preparing a synchronous counter, hardware count, it is going to be slightly complicated compared to asynchronous counter. So that you have to compromise with the synchronous and asynchronous counter. Sometimes people utilize the between the compromising these two, the combinational counter is also going to be utilized. The main difference here is that every flip-flop is triggered in a synchronous with the clock. In a synchronous counter, all the flip-flops are triggered in synchronism with the clock directly. That means clock pulse is given to all the flip-flops simultaneously, and after one propagation delay time, all the flip-flops changes the state, and hence they are synchronized, and hence glitches are going to be removed. Note that the stopping at the solutions of the glitch has been discussed in a previous asynchronous counter where unwanted signal was generated, which can be removed here, which we are going to study in this section also. See, this is the circuit diagram of modulus of 8 binary counter with parallel clock inputs. That means clock is applied parallel to the flip-flop A, flip-flop B, and flip-flop C. All the flip-flops J and K are connected to the VCC. That means these flip-flops are utilized in the toggle mode conditions only. So as soon as, and moreover, you can see at the clock inputs, there is a bubble. It indicates that all these flip-flops are changes the state on the negative edge of the clock pulses. So the first flip-flop, clock is given directly. So every negative edge of the clock pulse, the output of flip-flop A is going to be complemented. That you can see in this waveform also. At instead of time A, when the negative edge of the clock pulse is going to be there, output of A is going to be toggle. At point B also, at the negative edge of the clock pulse, the flip-flop A is going to be toggle. That means it is going to be complemented. Output is changing from high to low. At time C, again it is changing from low to high. That means output is going to be toggle every time there is a negative transition of the clock pulse occur. Now, what happens to the flip-flop B? You can see that directly clock is not given to the flip-flop B, but it is steered through the AND gate X to the flip-flop B. So when the output of A is going to be high, then the clock pulse passes through the AND gate X and available to the flip-flop B. So you can see that according to the truth table, when the B is required to be toggled, you can see that when the output of A changing from 1 to 0, B is required to change from 0 to 1. Again, when output of A is changing from 1 to 0, B is required to be toggled from 1 to 0. Again, you see that output of A is changing from 1 to 0, then B is required to toggle. So whenever output of A is going to be high, the clock pulse can pass through the X AND gate and it is triggered the flip-flop B, and the flip-flop B will be toggled after one propagation delay time. Same thing will be happen to the flip-flop C also. You can see that here we are utilizing the AND gate Y, which is having a 3 inputs. 2 inputs are output of A is one of the inputs, output of B is the another input, and clock is the third input to the AND gate Y. So when A and B is going to be high, the AND gate Y is going to be enabled, and because of this we can see that clock pulse is steered to the flip-flop C. So whenever A and B is going to be high, in this waveform also you can see that whenever A is high and whenever B is going to be high, the clock pulse is going to be available to the flip-flop C, and negative edge of the clock pulse at here at point D, the flip-flop C is going to be toggled. Again, when A is high, B is high, and negative edge of the clock pulse will occur, then the flip-flop C is going to be toggled. So the flip-flop C is going to be toggled at point D and H in this waveform C, which you can see here also that from 0, 0, 0, 0, it will be toggled after 4 clock pulse. That means flip-flop A is going to be toggled every clock pulse, flip-flop B is going to be toggled every second clock pulse, and flip-flop C is going to be toggled every 4th clock pulse. This is the way it is required and it is happening in this circuit. The construction of one type of the parallel binary counter is shown in figure 10.10 along with the truth table and waveform for the natural count sequence. Since each state corresponds to equivalent binary number or count, we refer to each state as count from now on. The basic idea here is to keep the J and K input of each flip-flop high such that flip-flop will be toggled with every clock negative transition at its clock input. We then use the AND gate to get every second clock to the flip-flop B and every 4th clock to the flip-flop C, and so on. This logic configuration is often referred to as steering logic, since the clock pulses are gated or steered to the individual flip-flops. That means this logic diagram or this parallel counter we designate as a steering logic parallel counter, because the clock pulses are steered to each flip-flop according to its requirement. Every second clock pulse is steered to the flip-flop B, every 4th clock pulse is steered to the flip-flop C. The clock is applied directly to the flip-flop A. Since the J and K input of the flip-flops respond to the negative transition at clock input and toggles when both the J and K inputs are going to be high. Flip-flop A will change the state with every negative transition of the clock pulse. So whenever A is high, AND gate X is going to be enabled and the clock pulse is passed through the gate to the clock input of the flip-flop B, and thus B changes the state with every other clock negative transition at point on a timeline B, D, F and H on the timeline. Since there is an additional AND gate delay for the clock at B flip-flop in comparison to the flip-flop A, it is not parallel counter in a strict sense of the term. That means total settling time is increased because of the gate propagation delay time also. So when you count the settling time, you have to count the propagation delay time of each gate also. Since the gate Y, AND gate Y is enabled and will transmit the clock to the flip-flop C only when both A and B is going to be high. Flip-flop C changes the state with every fourth clock negative transition at point D and H on the timeline. Examination of the waveform and the truth tables reveals that this counter progresses upward in a natural binary count sequence from count 000 to a count 111, or in a decimal 0 to 7 in upward directions, advancing one count with each clock negative transition, and hence we can say that it is operating in a count up mode. This is modulus of 8 parallel all synchronous binary counter operating in a count up mode, because there are 8 discrete states from 0 to 7 will be there. Let us see if this counter configuration has cured the glitch problem which was discussed in asynchronous or ripple counter. The waveform for this counter are expanded and redrawn in figure 10.11, and we have accounted for individual flip-flop propagation delay time here. Study this waveform carefully and note the following. The clock negative transition is the mechanism that toggles each flip-flop. So, when the negative transition of the clock pulse occurs or it will hit the flip-flop, then the flip-flop will be toggled because its J and K inputs are connected to the VCC or 1-1. So, it is working in toggle mode conditions. Second conclusion. Therefore, whenever a flip-flop changes the state, it toggles at exactly the same time as all the other flip-flops. In other words, all the flip-flops changes the state in synchronism. That means the flip-flop negative transitions will occur simultaneously to all the flip-flops if they are supposed to toggle. Then they are toggling in same time or in a synchronism, and hence the output waveforms are going to be glitch-free, or output waveform or a decoding gate are going to be glitch-free. As a result of synchronous changes of the state, it is not possible to produce a glitch at the output of decoding gate, such as the gate for 6 shown in a previous circuit, that is decoding gate 6. Therefore, the decoding gates need not to be stopped, which we have utilized one of the solutions to remove the glitch in asynchronous counter. All the decoding gates in figure 10.7 can be used with this counter without fear of glitches, and hence this output waveform from different decoding gates can be utilized as a control signal for further circuits. This is the circuit diagram or waveforms considering with the propagation delay time of each flip-flop. We want to decode the state number 6. The input of the decoding gate, AND gate, which is having a 3 input, A bar, B and C. So, here in the waveform, we have drawn A and A bar also. You can see that the output of the flip-flop A is toggling when each negative edge of the clock pulse occurs. But output will be resulted only after one propagation delay time. So, here after one propagation delay time, the output of A is going to be high. Again, on the next negative edge of the clock pulse, the flip-flop output is going to be toggled, but output will be resulted, or output is going to be complemented after one propagation delay time. This is going to be happen with every negative edge of the clock pulse. A and A bar is shown here. A bar is just exact mirror image of flip-flop A. So, they can be shown here. Now, when the flip-flop B is going to be toggled, every second negative edge of the clock pulse, the flip-flop B is going to be toggled. So, when the second clock pulse is going to be available to the flip-flop B, then after one propagation delay time, the output of flip-flop B is going to be toggled. You can see here that B is not going to be resulted at exactly same time the negative edge of the flip-flop A. but it is going to be resulted after one propagation delay time. The same time, every second, fourth, sixth, eighth, etc. negative edge of the clock pulse, the output of the flip-flop B is going to be resulted one propagation delay time. Similar things is going to happen to the flip-flop C. Every fourth clock pulse is going to be available to the flip-flop C. So on the negative edge of the flip-flop C, negative edge of the clock pulse, fourth negative edge of the clock pulse, the flip-flop C is going to be toggled, but the output is resulted after one propagation delay time. And you can see that this is the waveform for decoding gate 6, where decoding gate output is going to be resulted when C is going to be high, B is going to be high, and A bar is going to be high. Then during that time, the output of C is going to be high. So this is the output of state number 6, which was decoded. You can see that just like in a previous case, here when it is changing the state from 7 to 0, the glitch was produced in a previous counter, that is in asynchronous counter. In ripple counter, the glitches was produced because of different propagation delay time from different flip-flops. Here, all the flip-flops are changes the state simultaneously in synchronism with the clock. So when you can see that B and C is going to be high, the A bar becomes slow at the same time, and hence the glitch is already removed. So glitch is not going to be possible here. Note carefully that the external clock applied at either the count up or the count down input passes through the inverter before being applied to the end or circuit of each flip-flop input internally in the IC. Thank you.